In this video, we're going to review the derivatives of the inverse trig functions and the corresponding integral forms that we get from them. The first one is the derivative of inverse sine. Now, a word of caution here, that -1 does not mean an exponent. It means the inverse function of sine. And in fact, that can potentially avoid some confusion. It doesn't mean 1 over sine. It doesn't mean the reciprocal. Some books, and myself included, like to avoid that whole issue by using a different notation for the inverse sine function. And the notation I prefer, the term that I prefer, is the arc sine of x. So we're going to look at the derivative of arc sine of x. And if you recall from Calc 1, that's 1 over the square root of 1 minus x squared. There's a radical, so we want to make sure that what's under the radical is positive, and we certainly don't want it to be 0, or we'd be dividing by 0. And to ensure that's the case, you have to make sure the absolute value of x is less than 1, that the number x is between -1 and 1. Anything further away from 0, then those values will result in a problem when you try to compute this expression. So if I integrate 1 over the square root of 1 minus x squared, I should get, as its antiderivative, the arc sine function. The inverse tangent function, or arc tangent of x, it has a derivative of 1 over 1 plus x squared. Notice there's no radical now, and that expression is defined for all values of x. If I integrate 1 over 1 plus x squared now, its antiderivative should be arc tangent then. The next one that is useful is the derivative of inverse secant, or arc secant, and it turns out that it's 1 over x times the square root of x squared minus 1. There is a technical issue here. Depending on the book you use and how you've defined the inverse secant function, there may or may not be an absolute value here, and in the book that we use, there is absolute value. The reason for that is because there's two cases. The secant of a number can be positive or negative, and the absolute value here is taking that into account. So a bit of a technical issue, but just want you to be aware of it. That means if I integrate this expression here, I should get the arc secant back. Notice how in practice you're probably not going to see expressions with absolute values in the integral, but it turns out that it can be, in some sense, shifted over to the antiderivative here. So notice that the absolute value here is now in the arc secant function. So you should be roughly familiar with these three inverse trigonometric integral forms. And in practice, there's slightly more general versions of these that I want you to be familiar with. So I'm going to review now these generalized inverse trigonometric forms. And before I show you what they are, remind you what they are, let's look at a derivative problem. So I want to differentiate 1/4 times the arc tangent of x over 4. So it's basically differentiating the arc tangent of x, but I've got some constants in the way, so we just have to use the chain rule to see how to deal with that. So if I differentiate that, it's going to be 1/4 from the 1/4 here. I apply my derivative for arc tangent, which is 1 over 1 plus the quantity squared, and in this case it's x over 4 that's being squared. And then the chain rule says multiply by the derivative of x over 4, what's going into the arctangent function, and the derivative of x over 4 is just 1/4, so I get this extra factor of 1/4 now. So let's simplify this. It's going to be 1/4 times 1/4, that gives me 1/16, and if I square x over 4, I'll get x squared over 16. And then you can distribute that 16 through the denominator. When you do that, you'll get 16 times 1 is 16, and then in the next you'll get the 16s will cancel out, so you'll have x squared there. And you have now a nice simplified expression. Now let's think about what this means in terms of integration. If I integrate the answer I got here, 1 over 16 plus x squared, I should get what I had at the beginning, this complicated expression with the arctangent and these constants in there. So the point here is that if I'm integrating expressions where the number isn't necessarily 1 but is maybe something like 16, in this case 16 is 4 squared, it turns out that I should get a constant in front and a constant in the argument to the arctangent function. So if it's 16, I got 4 and 4, and it turns out that's because it's 4 squared. So if I'm integrating a squared plus x squared, where a is a number, a positive number, the answer will be 1 over a times the arctangent of x over a plus c. And again, a is the positive square root of whatever number you happen to have sitting there if it's not 1. There are analogous forms. You can play with, kind of do an example like we did above to see why they come out this way. For the arcsine form, if you have a squared minus x squared, it's arcsine of x over a. Notice there's no factor of 1 over a like we had in the arctangent. And for the arcsecant, the general version of this, now with an a squared instead of a 1 there, is 1 over a, and then it's the absolute value of x over a in the argument. Let's look at an example applying this. If I have 2 over x times the square root of x squared minus 16. So my a in this case will be 4, and if I apply the arcsecant form, I'll get 2 from the constant that I had here already, and then over a, so the a is 4, and then it's arcsecant of x over 4, just applying the formula plus c. And let's simplify that. I guess the only thing to do is just clean up the constants. It's 1/2. Okay, so let's look at just one more example where things are just slightly more complicated. Here I have 1 over the square root of 4 minus 3x squared. This basically looks like our inverse sine form, the arcsine form, a squared minus x squared. But notice that I have a 3x squared here, not just my variable squared. We know how to deal with a number there that's different than 1. That's what this formula tells us. So how do we deal with this 3? The answer is fairly straightforward. You just want to factor out the 3. So let's do that very carefully here. If I factor a 3 out of the expression under the radical, I need to account for that in the 4 by dividing by 3. So I've factored the 3 out of the x squared term. If I'm going to factor a 3 out of the 4 term, I have to now divide by 3. And if that seems confusing, go to the other way. Multiply through. 3 times 4/3 gives you 4. 3 times x squared gives you the minus 3x squared that you originally had. And this is good because when I'm multiplying under a radical, I can split the radical into 2 parts. It's really the square root of 3 times the expression here. And that square root of 3 is just 1 over square root of 3 outside the integral. And so now I have something slightly different than what we started with, but we can apply the general form to this expression now. The only thing is just figuring out what a is. In this case, a squared must be 4/3. So if I take the positive square root of that, it's 2 over root 3 is the number that we need to apply the formula with. And now it's just a matter of applying that formula. I have 1 over root 3 in front. The formula says now take arcsine of x over your a, which is 2 over root 3, plus c. And then let's just clean it up. We don't like this messy fraction here, so let's multiply by the reciprocal instead, and I'll have 1 over root 3 arcsine, and it'll be root 3 x over 2 plus c.